Another question I had this week actually works with the question I have here is what happens in a cell in a circuit. So when you're using an object, for example, your phone or remote for something, you have batteries. But if you have a unique cell, what happens here with respect to what's happening in the battery? And from there, I will go and expand to answer the question here about the tip for voltage and current. So let's see. And you'll see they all tie in nicely. This we need some insulators. Okay, so if you have a cell, which is a little battery, I don't have any here. We know that the end with the tip is positive and the other end is negative, like this. So here, how does this work? So we have a situation where we have a metal that has some electrons, but inside of the cell, we have what we call an electrolyte. Electrolyte, like this. The electrolyte, what it does, it looks like a toothpaste more or less in those cells. And what happens is that when you have the electrons on the edge here, the electrons goes into the electrolyte. And what happens is that there's an increase of the energy of that electrons. And what happens is the electron is going this way because this is a simplified version, but the metal here on the outside here is a metal that is strongly attracting electrons, whereas here in the middle, it's a different matter. And this one here welcomes electrons, but if something wants electrons more, electrons will go away. So what happens here, we have electrons that will here gain energy and ready for use. Now, electrons here, if we want to do something, so if we want to have some power, we need two things. We need the voltage, let's see, voltage, and the voltage here is the energy of the electrons. And then we need the current, which is the number of electrons. So these two are important because the more power I want, that means that I need more energy per electrons, or I need more electrons. And here we have an equation that is P equals V times I. So if I want more power, knowing that it's a multiplication, if I increase the voltage, the power will go up. If I increase the current, the power will go up. Often I give the example, if you are working and building a building or building a bridge, if you want to build a bridge with humans and workers, what do you need? You need workers, so a certain number of workers, but these workers need energy. You cannot build a building with 3 workers with a lot of energy. You cannot build a building with 1,000 workers with no energy. You need to have a number of workers that have energy, and therefore you have the power to do anything. So these are things to keep in mind. So voltage and current is important. We'll talk about it to answer the question in one moment. What is the next step here? So if it happens that I have a circuit that is open, I'm going to have a bulb here, and it's going to go this way. Here we have a cell that is stable, and in the conductors here, we have electrons that are present in the wire. Here we have a switch that is open. As soon as I close the switch here, something will happen. Here we have electrons that can start moving, not only in random direction, but because we have a positive end of the cell here, this electron will be attracted to this one here. These electrons will be attracted. So what happens is that electrons will start circulating because my switch is closed. And so the electrons are no longer erratic. We're going to go this way, and this way. What is interesting is that here we have tons of electrons available. They're going to go this way. They're going to go this way. So when the electrons are coming in, what will happen? The electrons are going to go here. They will have a chance to go in the electrolytes like this. As they go in the electrolytes, the energy will increase. And what will happen? We'll be able to do some work from there. What kind of work do we do if we have a bulb here or an LED? We end up with light. So what happens? We have here a battery where we have 1.5 volt of energy increase because it goes through the electrolytes. We have a closed switch, so the electrons are going to go here. They're going to give all the energy. So we have negative 1.5 volt, and then the electrons will continue, go to the cell, get energy, and be able to work as long as it's needed. So here the light will continue. So that's something to keep in mind. Great. I had a question about what prevents electrons from moving. And here there's another piece of information we haven't talked to yet, and it's about resistance. So resistance. So resistance is a property of matter that will take the matter, for example, in the bulb or the way it's set up, and it will slow down the electrons so that it can transfer the energy. Here we have chemical energy that will go into the electrons and will end up with light energy, and then we'll go on this way. Now there's a relationship between resistance, voltage, and current, and it's called the Ohm's law, and it's V equals, R times I. V here is the voltage, R is the resistance, and here we have units in ohms, the voltage units in V. Here we have I, and I here means intensity of current. And here the unit is in amps. Very nice. So the resistance is important because if we can slow down electrons the way we want, we allow ourselves to take the energy of the electrons when we want and the way we want to do some work. And that's how we can create, if you have our cell phones. So let's see, what image do I have? So if you take a cell phone like this, I have energy in the battery. A phone will allow me to have light for the image, to have sound waves. When I listen to someone, they'll be able to take my voice and transfer it into the system. I'll be able to have, sometimes the phone vibrates, so that's movement, and also the phone can become hot. That's thermal energy. So these are happening. And one thing that could be useful is what does affect the resistance? There are 4 different ways. One is the diameter of the conductor. If the more wire is thick, the more electrons will be able to go through, and there's less resistance. The next one is about length. The longer the conductor, the longer it will, the bigger the resistance. So if you think of our desktop, a desktop computer will create some heat. It has a volume. In order to minimize the resistance, what we've done is that we've miniaturized the circuits so that the length of the wires in the circuits gets shorter and shorter. That means that we decrease the resistance. Another one would be if you have a wire that is made of copper compared to a wire that is made of gold, for example. So copper is great. It's very conductive. We use copper in wires in our home to distribute electricity to do what we want. However, it is much less expensive than gold, and that's why we don't use gold in our homes, even though gold is a better conductor. What do we do, though, is that if we have a satellite, or we have, for example, connectors in a cell phone, and these ones are sold for quite a bit of money, what happens is that we have the opportunity to use gold, which is less resistance, less heat, but the quantity is so much less as well. So that's something to look into. And the other one here is about temperature. So if we have here a wire that gets warmer. So what happens? We have here, when it's cooler, we have many more electrons. And when it warms up, what happens is that the electrons are, the resistance increases, and therefore there's less electrons. It's not as efficient. For example, if you have a computer, if you have a laptop, they have little fans to make sure that it cools down the whole system, to make sure that your computer or your laptop stays working very well. So these are the 4 ways resistance is affected. So now that we've talked about a source, switch, conductors, and resistance, as well as a load, let's see if we can, at this point, answer the question or any tips on determining voltage and current. So let's see if I can do a circuit to show you what it looks like. I don't know if that makes sense. We'll have to figure it out because I just created this circuit. So let's see. So we know here we have one cell. So let's say that this is 1.5 volt. So that's the first thing to keep in mind. So if this is 1.5 volt and we have a lot of different ways, the best thing when it looks complicated is to find a way to simplify what you have. So for example, if you have a parallel circuit, you can certainly hide this part, and this makes it a much easier way to work with. If you are hiding this portion, then you end up with just something that looks simple here. Now you're going to say, well, this one here looks complicated. That is true, but you could decide to hide this part here and this part, and then you end up here with a smaller section. So the best way to answer it when it looks complex is to just hide the parts that you don't need and use the information you have at that time. So that is the point I have here. So let's see. If I have here 1.5 volt on the source and we have a parallel circuit, that means that we have all the electrons going this way will have 1.5 volt, and all the electrons going this way will also have 1.5 volt. So that's something we can look into because, yeah, you know what? I'm going to erase this one. Perfect. So here, this is something we can consider. We have this information based on what we have here. Now, there's other information we have. We know that we have electrons going this way, and there are 3 amps. Oops. There are 3 amps leaving here, the cell. If 3 amps are coming out, that means that there's also 3 amps coming in. So that's something that is useful. Now, interestingly enough, if I take away all of this, I know that at this bulb, you have 3 amp and you have 1.5. Let's see. Oh, not necessarily. So this is what I've got this point. So you have 3 amps right here. Okay, let's see if we can add more information. I'll see if I can find here what we're looking for. So here I have an ammeter that says 1 amp, and I have a bulb. If 1 amp is going through here, this bulb has 1 amp, and because electrons are going in, we have only one load. That means that it's 1.5 volt like this. So that's a good thing. So here I can now erase that. This is one piece of information I have. The only one I'm missing will be the resistance. So here I can use my equation, V equals R times I, to figure that one out. So if I'm looking for R, it's equal to V times I like this. So I have 1.5 volt divided by 1 amp. That would be 1.5 ohm like this. As I mentioned, I just invented all of this thing quickly. We'll see what the numbers end up. So here, this is the resistance on this port 1.5 ohm. I was able to find this based on the clue I had. Good. Interestingly enough, if I know that 3 amps are going here and going there, but I know that 1 amp is going here, that means that the number of amps going in this part here equals 2 amps, because you have 3 amps going this way, 1 goes up, and 2 goes this way for a total of 3. Then they meet here for 3. So that is a piece of information that I know without any problem. So that means that here I have 2 amps going this way, and very nice. Here I have 2 amps. Here I have here a resistance, which is 10 ohms. Very good. But I know that here I have a parallel circuit, but I know that on this one I have 2 amps. If the bulbs are the same in this example, so let's see, we have these bulbs here, and bulbs are the same. So what will happen is that the current is divided in 2. So this one, I have 1 amp here and 1 amp there. So there you go. So we are doing well so far. Okay. So here we had a bulb that had 1.5 ohms. I'm not sure if it would work mathematically, but if they were all the same, you could say that here we have a resistance. As I said, a resistance, if the bulbs are all the same, the resistance will be 1.5 ohm. Here we have the 2. Here we have resistance, which is 1.5 ohm. And here resistance, that is 1.5 ohm. So here, that will give us pretty much all the information we need. Because if you look and you divide it in small pieces, I have here the current and the resistance. I can find the voltage. Here I have the current and resistance. I can find the voltage. Here I can find the voltage, and here I can find the voltage here. So the question here is, are my numbers working? That's a good question. In a test or an exam, everything would work so that it works at the end. Very nice. Very good. And then resistance, 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 and we have this one here. So we would be able to answer all of the questions based on some of the clues we have. So as I mentioned, it was a great question here. If it's complex, hide the parts that you don't need, or look at the clues you have and see if you can spread out some of the clues. Now, if some of you are coming in saying the numbers are not quite all working, if it's 1.5, I understand, because I invented a circuit to show a complex circuit. I just wanted to know the premise on how it is, because I don't have a quick example with me right now. But hopefully in Tally, I was able to answer your question.